Hello, welcome to my presentation on using neuroevolution on checkers players. Just to start, I'd like to give credit to my teammates that I collaborated with on this project, who are Nikolai Binko and Guy Greathouse. So as introduction, checkers has been the focus of extensive artificial intelligence research. Um, this is because of its simplicity as well as the large number of applications. And so we used MMNeat, which is an algorithm for evolving artificial neural networks, to evolve an agent capable of playing at a high level. And so we ultimately ended up using expert knowledge about the game of checkers in order to design features which would help accelerate the learning process. So just as an overview, MMNeat is short for Multi-Objective Modular Neuroevolution of Augmenting Topologies. It's just a framework that builds on the basic ideas of NEAT. And so basically NEAT networks, they start small and simple, and then they grow more complex through structural mutations. And this NEAT algorithm is essentially, it's modeling evolution. And so there's natural selection, and it favors successful networks, and then also has random mutation in order to explore new possibilities and have hopefully find new more successful networks. And so this is the attempt to balance optimizing what you already have with generating a new diverse option, which could potentially solve the problem more effectively. And so just going through the overview of our general experimental procedure, three factors that we were changing in our experiment were the feature set that our players used to evolve, the opponent type, which was random or heuristic, meaning that the opponent either just made random moves or they made moves according to a heuristic, and then what heuristic the opponent used. And so we ran a minimax agent with a raw board game feature extractor and played against a random opponent. And this was our baseline for which we compared all future tests. And so you can see that in this top graph right here, what our win percentage looked like using our features versus the random player. And these features that we did use were these 9 features listed here on the poster, which were the count of the checks and kings for each player, the individual piece differentials for both types of pieces, the number of pieces that could capture an opponent's check, the number of pieces in danger of being captured, and the number of pieces on the edge of the board. So we first evolved the raw board state input against the sophisticated heuristic, and then we evolved our custom agent against the sophisticated heuristic. So here these graphs show the comparison of our player versus the random opponent, as well as the heuristic opponent over time. And so the interesting thing is we actually showed, at least at its peak, more success against the heuristic opponent. And this shows in our results where we achieved close to a 70% win percentage rate against a random opponent and an 80% against the basic heuristic agent for 100 generations. And so a reason for this is that potentially evolving against a random opponent, there's nothing that our agent is able to, it's harder for our agent to predict behavior, obviously, because it's random. And so our agent, it makes sense why our agent would potentially have more success against a heuristic player because it's able to predict the behavior more effectively. And so our results, obviously, they were not ideal because we would like to have much higher results against a random player as well as just a basic heuristic. However, our agent did show an improvement in win percentage, as demonstrated here, and fitness against the sophisticated heuristic compared to only the simple feature set of only raw board input. So our features improved our player. And our features, in essence, our features did have success in increasing agent performance against a strong opponent. And so, in essence, our project demonstrated the effectiveness of our custom feature set in comparison to the raw board state using MMNeat. And our project showed success in using expert knowledge features to evolve a checkers player. While demonstrating success, our results can be improved, and increasing generation size and adjusting trial and population size are small improvements worth trying in the future in order to improve our results. So thank you for listening.